diverse topics such as health, well-being, education, communications, scholarly sort, computer science, environment, etc. So it's research backgrounds in molecular modeling and equation of state for fluid mixtures. That includes a bachelor's in chemical physics from Sheffield and the PhD from Sheffield as well. All right, and a postdoc at UCD. All right, so without further ado, Daron Green.
All right. Great, thank you very much. I just want to start by saying that having a degree in chemical physics means I think I was hated by both the chemistry community and the physics community because you just don't fit in with either. But I was one of those people that put my hands up that I had no idea when I was studying that I'd end up eventually governing a lot of Microsoft Research's investments in universities around the world. But I couldn't be here without that scientific training, I can tell you. Okay, what I'm going to talk to you about is the strategy that we have for investing in collaborative and cooperative research and development in Brazil and Latin America. But really, to understand that, like any good student, I'm going to decompose the question a little bit. Because if I start on explaining what we do in this region without explaining what Microsoft Research does as a whole, you won't have that broader context. So first off, what is Microsoft Research? What does it do? Well, it was established about 24 years ago in a memo that Nathan Myhrvold wrote to the then sort of leadership team. And he said, look, we should have a capability of doing research to sort of insure ourselves against any sort of future disruptions. And within a year, Rick Rashid was hired from Carnegie Mellon University. He held the reins, controlled Microsoft Research for 20 years, and then more recently, Peter Lee, also from Carnegie Mellon, who took over in July of 2013. And the principles of why Microsoft Research were established are really here to advance the state of the art in the fields in which we do research, transfer that whatever that understanding is into Microsoft products, and then ensure both Microsoft and the field of computing have a future. So a lot of what you see Microsoft Research do actually is in this last category. We're investing in things to do with computer science. We publish a huge amount. In fact, that's the first priority for a lot of researchers, is to publish, and that helps further the areas of computer science in which we're active. And we know in the long term that that's going to benefit our products. And I'm going to give you some examples where that actually has happened. Some you may be familiar with, although you won't know necessarily all of the research that's gone into some of these things. We have research labs scattered around the world. These are primarily our blue sky research labs, and this is a historical view because obviously those all look like they're in the Northern Hemisphere. Still in the Northern Hemisphere, we have what we call our advanced technology labs that are a little bit more applied. And then most recently, about a year ago, I think we announced that we're establishing one of these advanced technology labs in Rio. And that's still in formation. So if you're interested, want to know more, please have a chat with me. Anyway, that's our footprint geographically. If you wonder, well, why are they in those places, then have a little bit more closely at the addresses of each of those labs, and you'll see they're right next door to really good computer science universities, okay, because we want to recruit great talent. What do? We research things that go into pretty much every single product that Microsoft produces. And the reason why it says nearly every product is because every now and then Microsoft buys a company, and when we've just bought that company, there's none of Microsoft Research's contributions in it yet. Okay, but sure enough, over time, typically we get something in there. We have about 1,000 PhD students, PhD card carriers. That's less than 1% of the population of Microsoft as a whole. Okay, so we're actually relatively small. In comparison, we generate over 20% of the intellectual property. So 1% of the population, but if you like, 20% of the brains. Don't tell the rest of the company I said that, by the way. All right, so a little bit more, what's our strategy, what sort of things that we do? And what I want to do is get quickly to an example, but really we do 4 types of research. We break them down into this sort of quadrant model. So on the x-axis, we think about things in either a short or a longer term, and then we think about whether it's reactive, so we're responding to an opportunity or responding to a competitive threat, or it's a more open-ended pursuit that we're engaged in. And I mentioned the sort of blue sky focus that most of the research labs have had historically. That's the sort of top right. And we might spend a lot of time, maybe 10 or 15 years, incubating a particular concept or idea for it then to get transferred into one of these other quadrants where we're perhaps working more in a more focused way with one of the product teams. And I'm going to give you an example. I'm not going to explain it on this chart, but I'm going to give you an example which resulted in the Kinect sensor. Okay, now, how many of you have had a play around with the Kinect? Hands up, show of hands. Okay, probably about a third. Or you've probably seen somebody jumping around in front of one of these. What I'm going to do is just explain some of the technology that's gone into that. And again, this is a 10 to 15 year computer science research effort over multiple different strands. Okay, so in a minute that's going to animate, I think. Is it? Whoa, don't want that yet. I'm sure there's a video going to play in a second, just when okay. At the top left there, maybe there's going to be a video that starts. What you're seeing is about 15 years, 10 or 15 years ago, the state of the art of what was called a depth camera. And that's the ability, if given a camera, for it to understand the depth of the scene that it's seeing. In this case, the very top left, you're seeing, around about 1995, the fact that we could separate somebody from the background and we'd have some understanding of the fact that the right hand there is slightly further forward than the chest. Towards the right there, what you're seeing is a segmentation of the body. So we're actually identifying different components that are going into the human figure and understanding how they articulate. All right. At the same time that we were going through that type of research, separating a person from the rest of a scene, understanding their physical attitude or configuration, what you may not be aware is that we were also doing an equivalent type of exercise, but in sound. Okay? And the very bottom left there, you see a microphone array. It's a little bit difficult to make out. And it's made out of something that I would call Meccano, or a metal construction set. There's about 8 or 9 different microphones all sort of together. So there's a microphone array. And what it's used for is if you position it in a room, it can help separate out where the sound is coming from and identify individual sounds across a whole range of noises that might be happening. So that was 1998. We refined it down in 2004, so it was in this simple strip. And then we combined it with depth camera technology to form the Kinect sensor. We call it a sensor, not a camera, because it does more than just take pictures. We combined it with the rest, so the vision capability, into the Kinect for Xbox 360. What you're going to hear now are 4 different bits of audio that show how we're able to separate out and clean up different types of sound. Okay? So the first one that I'm going to play is a fairly typical sort of sound. In my home, I have twin boys aged 13. Okay, so you will have heard a lot of action going on. There was a helicopter and there was a gun firing. You probably just made out a voice. Now, clearly there's a difference in where the sound of the game is coming from. That's coming from the TV itself, and then the person that's actually speaking commands to the console. So this is what the sensor is able to do in terms of sound separation.
Xbox, sign up. Xbox, switch profile.
Okay, so it cleaned out, just from knowing that these are coming from different sources, it was able to clean out all of the game noise. That's how you can play a game and still have commands heard. Now, this is a slightly different track. And what this is showing is the way we're able to just clean out background noises. Okay, and this might be some air conditioning that's running, or it might be the forced air heating system, or it could be your refrigerator that's humming in the background. Okay.
Xbox guide. Xbox mute mic.
Okay, and you hear that buzzing, you hear the humming. Well, listen how the sound changes when we really focus on that sort of individual's voice.
Xbox guide. Xbox mute mic.
Okay, so that's just one example of one bit of technology that's gone into the sensor. It's nothing to do with all of the rest of the sort of graphics capabilities and cloud services that go to provide that sort of computing and gaming experience that you have. So this was what we could do in 2010. All right, so that's 4 years ago. We have now the Xbox One in the market, and we have a more refined version of the Kinect sensor. And what I'm going to do now is show you a video of the sort of thing that we're able to do, the refinements that we can make in an understanding of somebody's position. Okay, and again, this is all computer science, but now we're coupling it with other modeling capabilities and some other sort of quite sophisticated things we're able to do with image analysis. Okay.
So my name's Kareem, and I get to talk about the brains. This is the really exciting part. This is where the full capability of Microsoft as a company all comes together. The engineers on our team get to work with top leading experts around the world in Microsoft research in fields such as computer vision, machine learning, speech recognition, facial recognition, digital signal processing, and we harness all that creative energy and innovation, combine it with the production engineering know-how on our team, and combine it into the platform that we're about to see today. I'll point out the anatomical correctness. His hips are in the correct location. He has multiple spine joints. He has true shoulders and collarbones, multiple joints in his head and neck. So he can bend over, he can bend forward, he can move his head, shrug his shoulders. So, you know, we're connected. The first version was really about understanding gross human motion. We have true human understanding here and fidelity of expression as he moves around. Another key advancement I'd like to point out is the new joints we added in the hands. We have joints that represent tip of hand and the thumb. So as Scott is opening and closing his hands, you can see it being represented on screen. So the skeleton is a great representation of the various bones and how they're connected together. But we took it a step further and started with orientation. Now, this is Blockman, as the team calls it. And what Blockman represents is the actual orientation of Scott's body as he's moving in 3D space. As he rotates his hands and his arms and his legs, you can see that Blockman is, very accurately depicting what he's doing. So we're kind of getting beyond the joints. We have the actual rotations that his joints are experiencing. He can even draw small nose circles in the air, and we can see his head rotating on Blockman in line with what it is that Scott's doing. Now, I'm a pretty tall guy. I'm 6'4". My skeleton only weighs 8 pounds. If you really want to understand what's going on in the human, you need to understand and describe what's going on with the muscles, the forces, the torques. So that's our intro into Muscle Man. So Muscle Man is a real-time human-based physics model applied on top of our next-generation skeleton and our high-resolution depth map. But what the colors represent is green equals no force, and then the highest intensity red is the largest level of force. As you see, as Scott kind of shifts his weight between one leg and the next, as he lifts a foot, you can see the red disc representing the greater force, on the floor being exerted. You can see changes in his core and his legs. If I can get Scott to do a little bit of a squat for me. All right, go ahead and hold it. Like he's feeling it in his legs, and you can see it on the screen. Normally I make him do that for a long time, but I'll go easy today. If we get Scott to jump up in the air as high as he can, you'll see that his body goes all green. When you're in the air, obviously there's no force being felt, and when he hits the ground, you can see those red impact points. Beyond just understanding the forces in his muscles, we're able to estimate, mass and velocity in the force of something like a punch. Give me a little jab. As you can see, the nice little white circles that represent how much he's exerting. Now really put your back into it and shift your weight. So look at the size of that circle. So we're accurately calculating how much force he's exerting. You can see the weight shifting from his back leg to his front. You can see his core tightening up, and you can see the representation on the screen. So with these three things combined, you have a fantastic understanding of what's happening with the human body. But as any good trainer will tell you, this information is necessary, but it's not enough. You need one more thing. You need heart rate. So what we have here is a real-time technology that is actually detecting the pulse in Scott's face. We're using our high-definition color feed and our active IR feed to look for subtle variations in both color and intensity in the skin of his face. They're imperceptible to the human eye, but our Kinect sensor and the Xbox One hardware is able to pick it up. We're literally reading the pulse in his face. Pretty amazing stuff. Fantastic for exercise scenarios or for measuring exertion. Lots of possibilities.
Okay,
My name's great, and I get to talk about the brains.
Oh, he's going again.
This is the really exciting part. This is where the full
Stop, Kareem. Okay. So that gives you some taste of what we're already able to do in the sensors that we've just released. And as you can imagine, the new sensor was released about 18 months ago, and we're working on what the next generation's able to do. A lot of what we're coming up against goes beyond computer science now. So we're getting into physics models there. We're getting into some understanding of the human anatomy, and that goes well outside what Microsoft is able to do on its own. And that brings me to some of the cooperative research and development that we need to do. I'm going to change topic just a little bit and talk more about some of the hardware, the sort of more traditional computing hardware that you may be familiar with from Microsoft. So this is a Surface, is actually a Surface 2. We've now got Surface 3s in the market. What we're trying to do is make it more natural to interact with those in the same way that we've provided a more natural interaction for folks that are gaming. We'd like to take some of that technology and incorporate it into this sort of computing platform. That's pretty hard to do for a range of different reasons. We still want it to be lightweight. We want to have a great battery life. We want, if you touch it, for it not to get greasy. Okay, we want it to be oleophobic. Lots of things that, as somebody that understands the sort of chemistry and physics of how these things are used, are relatively challenging for the sort of material sciences space. So what are we ourselves experimenting with? Well, here's an example of some of the stuff that we're incubating at the moment. This is a display system. It just looks like a flat piece of perspex, and we're shining light into the bottom of it, and we're able to direct where it comes out. Okay, so the light is actually shone into the very bottom. You can't really see it because it's bleached white, and then we're projecting it out just from that display out onto that screen. Okay, now if we're able to project in that way, then we're actually, because of the properties of light are reversible, we're actually able to see as well. So these pictures were taken from a flat display, okay, where we read in at the edge of the display what the image is or what's in front of it. And you can see actually on the left-hand side, those are infrared images, and then bottom right, that's obviously in the optical, and you can see that we're not just able to see directly above the sort of perspex surface. We can get actually some quite, I mean, it's not very clear, but this is still in the sort of prototype phase. So this is us just using a flat panel, both to project from and then to take an image from. Okay. I want to give you now an example of some other work that we're doing. I'll probably break this off partway through because the video is a little bit long, of the ways in which we're sort of combining some of the technologies that you've seen. So in this case, what we've got is a beam splitter. So this piece of perspex is actually splitting a beam that's being projected down from above. There's a Kinect sensor above that's looking at the sort of context of the hand, the cup, and the piece of paper. And then we're projecting on top of that the ball or whatever the objects are that the user's interacting with. Now clearly the user senses nothing from the fingers, but visually they can actually see a proper sort of 3D image. So this is where you see the projection system down, the beam splitter. An important thing here is that we're using the Kinect for face tracking. So without the face tracking, you'd see a huge parallax, but with the face tracking, it makes sure that the image is projected over the top. And there's the Kinect sensor at the top doing that face tracking. And for those of you that are genuinely working in the sort of physics domain, a lot of the things that you're seeing here, the fact that we're modeling things as particles, looking at flow, you'll recognize from things like finite element analysis or computational fluid dynamics and these sort of models which we're using to build a real world understanding of the fact that there's a piece of paper there and it has certain properties. Okay, I'll break into that and just move on. So that's great, it looks like we're really good. We are, but we have a lot of things that we can't do well. We still can't make the sort of system that you're looking at really light and thin and low power. We'd like to have some of the sort of backlighting capability that we're using on a lot of our displays to become films rather than sort of solid sections that we're building at the moment. The display systems, we're already able to do visual steering, and what that means is that if two people are looking at the same screen, we're able, if they're sitting side by side, to track those two people and then let each of them see something different. Okay, so two people playing the same game, even on a full large screen, would see two totally different perspectives. So we're already able to do that sort of visual steering. But we'd like to be able to enable things like multi-view, increase the amount of gesture and touch that we're able to do, and also integrate other modalities of inputting information from things like pens that are integrated into display. So we're actively looking for partners worldwide for all of these areas. Okay, so that was me talking about corporate R&D in general. What I want to do now is focus a little bit on what we've been doing in Brazil and Latin America, and there's a couple of things that I'll highlight. So you may be aware of a very large shift to cloud computing that's happening in certainly the IT domain. A lot of commercial customers are moving to the cloud. Actually, not that many researchers have been moving. So about 18 months ago, we piloted here in Brazil our cloud computing for research efforts. And we ran our first training actually here in Campinas. So this was October of last year. We had about 56 participants, most of which were from the state of Sao Paulo, a few from some of the regions and a few from some of the countries. Actually, Uval, who's the trainer here, is up in Porto Alegre today, giving some more training. He's at Recife on Wednesday, and I forget where he is on Friday. So this is a good example of where, from a regional perspective, our strategy has been to come and trial things here in Brazil first. Okay, and there's an interesting reason for that. There's an appetite and a hunger for things that are new here, and a willingness to partner that we don't see in some of the other countries where we do have collaborations. So this was great. This was a sort of pioneering things initially. The same platform that we use for that training, the same platform that my kids use for running a Minecraft server, okay, was used by some researchers within Microsoft to run over 27,000 cores, and about 63 billion pairs of genetic markers were analyzed. Okay, and the reason why I'm mentioning my kids and this, if you like, supercomputing experiment is that it's exactly the same platform. That's why cloud computing, I think, is so interesting, because now everybody can get access to a very scalable compute capability. So again, we piloted the use of this for a research platform here, and we issued a number of awards. So this is where people that had done the training, and those that hadn't, but predominantly those that had come and done the training with us, could get access to the platform for free for a year. And this was the response rate. Now, you won't have a chance to read all of the numbers there, but there's about 155 applications that we received, and we granted about 75 awards. And currently, Brazil dominates the use of our platform from a research perspective, okay? Which is, I mean, it's interesting from the point of view that we have a cloud computing data center here in Brazil, but other than that, you have relatively modest access to cloud computing. So it's a huge movement for you. Okay, still on the sort of cooperative R&D in Brazil and Latin America, a flagship engagement for us has been the relationship that we have with FAPESP. So it's not by coincidence that we did the training here in Campinas. We have a lot of good collaborations in the state. Here at Unicamp, USP, and so on. These projects are not just in computer science. Yes, a fair number are, but we have them in biology, health and genomics, agriculture, climate change, biodiversity. And this speaks volumes to why we're doing these collaboratively, because we're not experts in all of these other fields. We're interested in the challenges, we're interested in the data sets, we're interested in the scientific problems, but what we can bring to bear are some really good computer science algorithms, some great computing infrastructure, and maybe some different ways of thinking about things. So we address unique problems that require our expertise, but really rely on the fact that there's other scientists at the heart of this. And why do we do this? We do it, yes, because we want to try and solve some of these problems. We also, to the point that was made by one of the earlier speakers, we know we're in a competitive market for talent globally. Okay, so we want early access to those great brains that there are in this region, in this country in particular. And this is how we do this. This is how we get to interact with students. A lot of the professors that we deal with here will send students up to some of our labs to take internships, and that's a way for them to get to understand what it would be like to come and work at Microsoft, what it's like to be a computer scientist or work with a computer scientist in a major corporation, and it de-risks that hiring problem of will it work out for the individual and will it work out for Microsoft. Okay, so that's why we do it. I'm very lucky that about 6 months ago I asked my team to put together a video, not knowing I was going to come and present here, but I asked them to put together a little video that summarized the relationship with FAPESP and focused on one of the projects that we have in flight at the moment.
FAPESP is a research funding agency in the state of São Paulo, Brazil. It funds research in all areas of knowledge. Microsoft Research and FAPESP started collaborating as a joint research center back in 2006. We work on a call for proposal basis, so researchers from the state of São Paulo are invited to submit proposals, and we co-fund research.
The FAPESP Microsoft Joint Research Center is a collection of research projects which are selected by FAPESP and by Microsoft Research, mostly in fields related to the environment.
Our objective is to somehow assess the impact of climate changes on plants. My role in this project is to develop a set of computer science applications, tools, and algorithms that could help in the data analysis and data acquisition and also in the data mining process. In this project, we have two teams. The first one, based on UNESCO University, is in charge of the technology aspects. The second team at Unicamp in the Record Lab is in charge of developing the computer science tools.
Pathology is the study of recurrent life cycle events, such as the flowering, leafing, bird migration, and its relationship with climate. And that's why phenology is nowadays one of the best indicators of climate change. Traditionally, the phenology is done on the ground through on-the-ground observations, and this takes a lot of time. We have an phenology core site, which is in the Serra do Solano. And in this site, we have the tower with the digital camera photograph the vegetation, and then we take daily photographs of the vegetation, and we can see the changes on the vegetation. And we validate this camera data with this on-the-ground observation. Phenology compared with the traditional on-the-ground phenology is much more efficient. We can have much more information with less human labor, but also one thing that is very important is that we can repeat that over a large number of sites, what is nearly impossible with this on-the-ground traditional phenology.
We have different outcomes in this project. From the computer science perspective, we have been developing some algorithms for image processing, data analysis based on database features, also some techniques based on machine learning approaches. From the phenology perspective, we have been developing some models to establish connections between image features and phenology data that have been obtained.
The Joint Research Center provides two main benefits for us as researchers. The first one is allow us to do risk research on the edge of knowledge without constraints. And the second one is put us to work together with computer scientists, which expand our possibilities to answer questions, analyze data, and open up a lot of new horizons for our research.
So that's a win-win. We can focus on problems that are strategic, very relevant to the humankind, and at the same time, those problems pose a challenge to computer scientists, and we can advance the state of the art in computer science.
If you invent a new tool that can observe or measure something nobody could do before, that's when you have a chance of doing new science.
This new generation of researchers, they're going to be, I believe, much more skilled than the previous one we had, because they are being trained in the skills from plant ecology and from computer science. So we are building up a new generation of researchers through this joint research center.
So just in summary, I realize this was a very quick sort of run through the portfolio of things that we have within Microsoft Research. So just to highlight again, we're one of the largest computer science research organizations, arguably the largest in industry. We're investing in the region, in part because we're trying to recruit all the talent we can, but also because we want to solve some major scientific problems. And a lot of these are pushing the boundaries of our technology that eventually we want to try and weave into our products and services at some time. With that, I'd like to say thank you, and I'll take any questions.